Hey everybody, today we're going to be talking about trig proofs. This is the first day that we've done on trig proofs, and I feel like this word proof scares people. Maybe it's because you had a bad experience in geometry, maybe you've tried proofs before and they've been really hard, but really all it is just using algebra to get from one side to the other. So let's just kind of look at an intro to what a proof is. So what is a proof? Well, a proof is where you're given something that's true, but it's not necessarily obvious. So it could be might call it a statement or a sentence or a mathematical expression, or sometimes you'll hear it called an identity. But it could be just something like this. This is just an algebraic statement. X squared minus 1 over x minus 1 minus x squared minus 1 over x plus 1 equals 2. So the advantage to doing these proofs is that you know what they're giving you is true. And all you really have to do is show logically that you can get from one side to the other. I mean, just looking at this doesn't really look like it makes sense. It looks like something we might have to solve for x. But this is something that is always true. It's an identity. And so what we have to do is we have to show how you get from one side to the other, and that's what your job is. So your job, this will move forward for me. There we go. So it's your job to get logically from one side to the other, showing all your steps along the way. And the way the book says it is anyone with a general understanding of algebra or trig should be able to follow your proof. So you can't just write this down and say, obviously this is true. You have to show some algebra how you get from one side to the other, and we're going to do that on the next slide. So you can start from either side. Generally, you want to start from the more complicated side. So right here, I would say your more complicated side is definitely the one with all the x's. It'd be difficult to start from 2 and then somehow show that you get to the left, and we'll show that on the next slide as well. What you can't do, and this is a mistake I see a lot, is you can't work from both sides and meet somewhere in the middle. And that's kind of a way that some students try to kind of cheat the system. They kind of say, well, I did some stuff on the left, I did some stuff on the right, and now they equal each other. Or maybe they don't quite equal each other, but they make it equal each other, and you can kind of try to scoot around by doing that. But you have to start from one side, do step, 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 and then end with the other side. That's the goal of a proof. So let's try that algebraic one that we were looking at. We're going to prove that this is always true. No matter what x value you use, as long as it's in the domain. So in this case, clearly x could not be x couldn't be 1 because we would be dividing by 0 here, and x could not be negative 1 because we'd be dividing by 0 here. But for any other value of x, this should be true. And let's see if we can prove it. So we're going to start with the left side. So I'm just going to write it out again. So we have x squared minus 1 over x minus 1 minus x squared minus 1 over x plus 1 is equal to... So now what we're going to do is we're going to just set this, we're going to start doing steps with this left side, and we're going to try to make it equal to 2. So what I see right away is that the top on both of these fractions are differences of squares, so I can factor them. So x squared minus 1, that's x plus 1, x minus 1. Okay, you need to brush up on your factoring, let me know. And that's still divided by x minus 1. Oh, that's nice. Looks like something's going to change there. And then we're subtracting x plus 1, x minus 1 over x plus 1. So that was our first step, and anyone that knows algebra should be able to see, oh, you just factored the top. So that's all our first step was. And in the book, actually, if you read some of the examples, they write next door kind of what the steps are. So they would put in parentheses factoring. You don't have to do that. Like I said, as long as anyone reasonably knows algebra is going to be able to follow your steps, you're just fine. So now what I'm going to do is, well, I have some common factors on the top and bottom that I can cancel out here. So I'm going to cancel out the x minus 1s here, so I'm just left with x plus 1. And then I'm subtracting off. Looks like the x plus 1s cancel here. I could put these in parentheses if that makes it easier to see that they're canceling. So we canceled these. We canceled these. So we're left with x plus 1 minus parentheses x minus 1. Now the parentheses are important because we'll have to distribute that negative sign. That's just an order of operations thing. So all we did there was we canceled a common factor. Cancel common factor. Excuse my handwriting. Hard to write on the screen here. Okay. So we canceled the common factor there. And now we're just going to distribute that negative sign. So this is x plus 1 minus x, and then that's going to be a plus 1. So that was just distributive property. Distributive. And now it looks like those ones are going to cancel, or the x's, excuse me, are going to cancel. So the x's cancel, and I'm left with 1 plus 1, which is 2. And then there are lots of ways to end a proof. You can kind of find the way that is your favorite. In all of my solutions, you're going to see me use a check, at least on the packet that you're going to do today. Some other fun ways to end proofs, maybe I'll just do them one at a time. We're going to do some more proofs, so I'll kind of unveil them as we go along. I bet you can't wait. The suspense is just killing you. So now that we're getting into trig, these are some trig identities you're definitely going to need to memorize. We showed how all these came from the unit circle. We used similar triangles to show that tangent was sine over cosine, and then cotangent is cosine over sine. Those were kind of simple ones. We used the first quadrant of the circle, and we said if this is where we're at, then we use different color here. The red right here would be your sine value, and the green right here would be your cosine value. And then if you extend out the purple line out to maybe where it would meet a tangent line, then your tangent value is this guy right here, and since this is 1 on the bottom, we were able to use similar triangles to show this was true. And then this purple value right here, that's your secant value, so we're able to show all of these using the unit circle. But now we just need to know these right offhand. So tangent is sine over cosine, cotangent cosine over sine, right? Those are reciprocals of each other. Cosecant is 1 over sine x. Secant is 1 over cosine x. So if you want to write these down, you can, but my guess is most of you know these already. And these are some that we haven't really seen before. So because cosecant is 1 over sine, we learned this trick back when we were doing logistic equations. You can just switch the left side and the denominator. You can just swap them. So sine is also 1 over cosecant. I mean, you can think about that for a second. If it's 1 over sine, dividing by a fraction is the same as multiplying by its reciprocals. This is 1 times sine x over 1, which is just sine x. Okay? Cosine x, then you can do the same thing. You can just swap the cosine with the secant, so cosine is 1 over secant. Those two you don't use a whole lot. Every once in a while you might see a proof where you have a 1 over a secant, which you can turn into a cosine, but not all the time. And then tangent is 1 over cotangent. That makes sense because these two are reciprocals of each other. And then cotangent is 1 over tangent. So these are kind of 8 building blocks, you might call them, building blocks, that are going to be useful in all of the trig proofs that we're going to see today and in the rest of the unit. So let's see how we can use these things. Let's get to our first trig proof. Hooray! So we're going to show that tangent x cotangent x is equal to 1. Now we're going to start from the left because we have our more complicated side here with tangent x cotangent x. But for this proof, I'm going to show how you could do it both ways. Okay? So we're going to do a left to right, and I'll also show you a right to left. And you'll see that starting from the left side is much easier than trying to fabricate this 1 into something that's going to make a tangent x cotangent x. So if we go left to right, tangent x times cotangent x, a good strategy here is just to put everything in terms of sine and cosine. So we have tangent x cotangent x. I'm going to write this equal, so I can't jump right to here. That's not obvious. So I'm going to write this in terms of sine and cosine. Well, according to our identities on the last slide, tangent x is sine x over cosine x, and cotangent x is cosine x over sine x. Now, right away, you can probably see the cosines will cancel, the sines will cancel. I'm going to throw in another step. It'd be okay. I think it'd be okay for you to write that this, you could just cancel them right here and say, hey, that's 1 times 1, which is 1. I'm going to throw in another step here just to really show clearly what's happening. So I'm going to use the commutative property of multiplication. So you can switch how you multiply these things, right? So this is sine x times cosine x over, now I'm going to swap these. So I do sine x times cosine x. Okay, so that was the commutative property. I just multiplied across because they're fractions. You can do that. And then I changed the order of the sine and the cosine to make it really clear that these will cancel, these will cancel. So that's just 1 times 1. You could probably even skip that step, which is just 1. Okay, now another way to end a proof, one that I like a lot, is called the proof square. You just make a little square, and then you shade it in. And that shows that you are done with the proof. Okay, so if you like the proof square, you can do that. And that shows that you have started from the left and gone to the right. Now, if we went right to left, we have to start with 1. Okay? And now you can see the problem already. Really, there's not much you can do with 1. But what I could do to write 1 as, I could say, okay, well, 1 is 1 times 1. And another way of writing 1 is sine x over sine x, because they would just cancel, as long as x isn't 0. Because if x was 0, sine of 0 would be 0, or pi, or any multiple of pi. Not going to worry too much about the domain here, though. Then the other one I could write as cosine x over cosine x. And now I'm going to use that commutative property of multiplication again, where I'm going to write this as sine x over cosine x times cosine x over sine x, which ends up being tan x cotangent x. Another way to end a proof, sometimes people just use a slash. Shows that you've basically come to the end of your work and you have nothing else to show. So this way, I mean, weird, right? Because why would you ever make a 1 more complicated? It's usually better to start from the complicated side where you have lots to work with and then move towards the easier side to deal with. But it's up to you. You can do it either way. So let's look at another trig proof. Another multiplication one. So a few things, I chose this one specifically because it shows a couple things that you need to be able to see. One is that this notation, we talked about this a little bit the day that we proved, I think it was law of cosines. I think we might have also used it in the law of sines, but when you have sine squared, this is the same thing as writing sine of x squared, or writing sine x times sine x. Okay? The reason they do the square like this is because when you have sine x squared like this, you're not sure if you're squaring the x first or if you're taking the sine and then squaring it. So for example, like if you had sine of, let's say, pi over 6 squared. If you wrote it like this, I don't know if you're taking the sine of pi squared over 36, which would be really hard because we have no idea what that is, or if you're first taking the sine of pi over 6, which is easy. Sine of pi over 6 is 1/2, and then squaring it, which would just be 1/4. These are very different things, which is why they tend to put it in here to make it very clear that we're doing sine x times sine x. So that would be the 1/4 situation where we have here. Okay? So you want to be very, very careful about how you put your square on there. This is the notation that you're going to see used all the time in the book and that you'll see me using as well. The other thing that's important in this proof is that we're going to be showing some division by fractions, which is where you can really show off your algebra skills. So let's try this proof. We have sine x over cosecant x equals sine squared. I definitely think the left side we're going to be able to do something with. The right side, sine squared, there's not much we can do with that. So let's take a look at the left side, this sine over cosecant. So I'm going to rewrite it. Sine x over cosecant x. Now we're going to use one of the identities. The cosecant is 1 over sine. So here we have sine x over 1 over sine x. Now this is a strategy that you're going to see a lot when we divide by a fraction. That's exactly the same as multiplying by its reciprocal. So I'm going to rewrite this as sine x times sine x over 1. You wouldn't need to do the over 1. I think most of you know, and anyone that reasonably knows algebra should know that sine x over 1 is just sine x. But I'm going to put that in as another step. So that's sine x times sine x. More steps is always better than not enough. So sine x times sine x, that's exactly how we just defined sine squared x. So that is sine squared x. Okay. Another way to end a proof, W5. So I'm going to put the 5 next to W, or you can put it a little bit lower. W5 stands for which was what we wanted. Okay, 5 W's. So if you like the W5, it's a nice way to end a proof, which was what we wanted. If you want to make up a way to end a proof too, sure. You know what? Go ahead. Be creative. It'd be fun to see how you guys can come up with some endings of proofs. As long as you tell me what it means, I'll know that you've ended your proof. Okay, so it's division by a fraction multiplied by the reciprocal. Not too bad. So really the first, maybe, is it 6 or 8 problems on your green packet have to do with kind of problems like this, where you're multiplying or dividing by things only, no addition or subtraction, so it's not too bad. Now we're going to get into some stuff where we're going to be adding and subtracting these things, which is going to be a little bit more complicated, but still not really too bad. So let's take a look at this one. We have tangent x plus cotangent x equal to secant cosecant. So this one, some people might argue that each side is equally complicated. I'm going to use the one with the addition sign, because in general, when there's an addition, you can do some like finding of common denominators kind of thing to be able to try to get it to a side that's just multiplied together. So let's start with the left side. So we have tan x plus cotangent x. And I'm going to write that in terms of sine and cosine. So this is sine x over cosine x plus cosine x over sine x. Now, as excellent students of algebra that you are, To add two fractions together, we need a common denominator, which right now we don't have. So to get a common denominator, I'm going to have to do some multiplication here. Now you could just write it on the same line. I'm actually going to do it as a new step. So it looks like to get a common denominator here, I'm going to have to end up having it as sine x times cosine x. So this first one I'm going to multiply by sine x on the top and the bottom. So I have sine x times sine x over sine x times cosine x. Excuse me. And then we'll have plus, excuse me. Yep, still plus. No. We'll have cosine x times cosine x divided by sine x times cosine x. Okay. So we have our sine times sine, our cosine times cosine. On the bottom now we have that common denominator. So I'm going to rewrite this as sine squared x plus cosine squared x divided by sine x cosine x. Now, this top that we have here, this is something that we talked about when we proved law of cosines. And we said that if you're in the first quadrant, or any quadrant of the unit circle, and you think about your sine and your cosine, use some different colors for this again. I'm going to use red for sine, that's what I did before, and then green for cosine. So down here, that right there is our cosine x. The red is our sine x, right there. And then that purple value is the radius of the circle, which is 1. So if we use, this is a right triangle, so if we use Pythagorean theorem on this, we have cosine squared x plus sine squared x is equal to 1. And when I see you guys again after I'm back, I'm going to show you some other identities with Pythagorean that come up really nicely. Today I just want to show you this one. You actually won't need this in your green packet at all, but in this problem we need it. So if cosine squared plus sine squared is 1, that's exactly what I have on the top here. So this is just 1 over sine x cosine x. Now I'm going to split that up. So this is 1 over sine x. I'm actually going to write it as 1 over cosine x times 1 over sine x, which is secant x cosecant x. And for this one, I'm going to use QED. QED is Latin, which means quod erat demonstrandum, which I believe means what we wanted to display, or what the goal was to display. I'll have to have my Latin students check me on that, but I think that's roughly what it means. It was what we wanted to demonstrate. And so that idea of using sine squared plus cosine squared to make 1, again, you won't need it on your packet today, but we'll talk more about it when I see you guys again. And then the splitting up, so we had to split it up across the multiplication of fractions there. So a couple little tricks in there, but nothing too bad. Now if we had gone the other way, think about it. If we'd started with secant, cosecant, and gone to the other side, we would have gotten to here, and then we would have had this, but we would have had to realize that 1, in order to create these tangent and cotangents, we would have had to change that into sine squared plus cosine squared, which can be tricky, because when you see 1, it could be so many things. It could be a fraction in and of itself, or you could choose this Pythagorean identity. There are a lot of ways that that could go, so it's easier to start from the left side with the addition. Cool. So, we're going to talk a little bit more about using that form of 1 in the next problem. So we have here, something that looks pretty complicated on the left, so we're definitely going to start there. And we're going to use these 1s in kind of a more creative way to show that this is equal to tangent x. So we're going to start with the left side. We have 1 plus tan x divided by 1 plus cotangent x. And let's see what we can do with that. So that'll be, let's put it into sines and cosines. So we have 1 plus sine x over cosine x. And that's divided by 1 plus cosine x over sine x. Now, what we'd like to do is combine this top together. So we need a common denominator between 1 and sine over cosine. Well, 1 can be the same thing over itself, no matter what it is, right? 1 is x over x, as long as x isn't 0. And so I can put the same thing over itself. So if I need a common denominator of cosine, a really good thing to do there would be cosine over cosine. So let's change that 1 into a cosine x over cosine x plus sine x over cosine x. And then what do you think we need on the bottom? Well, if we need that common denominator of sine, what should I turn that 1 into? It's going to have to be sine over sine. So on the bottom, we have sine x over sine x plus cosine x over sine x. Now let's combine those. So on the top, we'll have cosine x plus sine x divided by cosine x. And on the bottom, looks like we'll have sine x plus cosine x divided by sine x. Now we're going to use our idea of dividing by a fraction. So remember, this is our main division line here. So the top is a fraction, the bottom is a fraction. So let's, instead of dividing by a fraction, let's multiply by the reciprocal. So we have cosine x plus sine x over cosine x multiplied by, looks like sine x over sine x plus cosine x. So you can kind of start to see what's going to happen here. This cosine plus sine and this sine plus cosine, those are the same thing. So sine x plus cosine x plus sine x are exactly the same thing. So I'm going to actually pull those to the left side. You could at this point just cancel those out, but I want to be very clear about what's happening here. So I'm going to write cosine x plus sine x. Now I can use commutativity to rewrite this as cosine x plus sine x. And then it's multiplied by sine over cosine. So just some commutativity of both multiplication and addition that I used there to rewrite that. Well, the left side here just cancels. Same factor on the top and bottom, so they're gone. So we'll sine x over cosine x, which is tangent x. Okay, I'm going to use a line on that one. Okay, so tan x is the same as the left side, as long as we're in the right domain there. So that idea of using 1 and rewriting it as the same function over itself, you're going to use all the time, and you need to understand how that works, because if we need that common denominator, we have to change that 1 into something where we can combine those fractions together. Otherwise, please, please, please don't do this. This is a really common algebra mistake. This is not 1 over 1 plus tan over cotangent. Right? That's not right. That's a big no-no, because you can't split that across the denominator. You can't do that. You can split it across the top. You could change this to 1 over 1 plus cotangent x plus tan x over 1 over 1 plus cotangent x. But that doesn't really help you out a whole lot. 1 plus cotangent x. This doesn't help you. Really, we want to try to get this into a single thing. So splitting it into two fractions here, not going to help us much. Okay? So in general, you just want to be able to combine those right off the bat. Get rid of this so no one does that. Okay. All right, I think that was my last example for you. Now I just kind of have some general strategies that we used today that are going to help you out. So first strategy we had was put everything in terms of sine and cosine. So that's really why those identities on our first identity slide today are going to be useful. Secant is 1 over cosine, cosecant is 1 over sine, that kind of stuff. Tangent sine over cosine, cotangent's cosine over sine. So if you put everything in terms of sine and cosine, going to make your life a lot easier. Dividing by a fraction, same as multiplying by its reciprocal. So if you have 1 over tangent x, first put it in terms of sine and cosine, 1 over sine over cosine, which is the same as 1 times cosine over sine. Put x's on those as well. Okay, so dividing by a fraction, same as multiplying by the reciprocal. It's important. Common denominator. So if you have 1 plus secant x, that's 1 plus 1 over cosine x. So I'd change that 1 to cosine over cosine. Plus 1 over cosine. And now you can add across the top. So that would be cosine x plus 1 over cosine x. So common denominator, really important there. If you have to multiply both by something to get a common denominator like we had to do in our first tangent plus cotangent, then that is also useful. Also turning 1 into a fraction. So that's what we just did right here, right? Turning that 1 into a cosine over cosine so you can get a common denominator. That's just a special case of doing that common denominator right there. So if you remember these strategies, you're going to be in good shape, and you should be able to do your green packet now. So make sure you got that from the sub. Take a look at that green packet, and you should be off and running on how to do trig proofs.
We're going to learn more strategies later this week, some more stuff with doing Pythagorean identities, also looking at factoring things out of trig expressions, basically pretending like sine and cosine are x's and y's. So got that to look forward to. I will see you guys when I'm back. Talk to you soon. I love you guys. Have a great day. Bye-bye.